Hello and welcome back to Functional Analysis. And as always, I want to thank all the nice people that support the channel on Steady or PayPal. Today's part 6 finally is about Banach spaces. We will later see that a so-called Banach space is indeed one of the most important objects in functional analysis. In its core, it's just a vector space, but with more analytical structure on it. In order to understand such a Banach space, we first have to define what a norm is. For this, I will use the letter F to denote a field of numbers. However, here it will always be the real or the complex numbers. Of course, this makes our life easier because we don't have to write down the definition 2 times. Now we have a set X that also carries some operations such that it is a vector space. F vector space always means that the scaling of vectors is done with numbers from F. This means if F is R, you can scale with real numbers, and in the case that F is C, you can scale even with complex numbers. The usual visualization for points in a vector space is given by arrows. It's a good idea because you see the 2 operations scaling and adding to vectors immediately. However, from the analytical point of view, it would be also nice to know how long such an arrow is. Measuring such a length is what we call in the abstract sense a norm. The symbol one uses for a norm are just 2 lines on the left and 2 lines on the right. And because we are measuring a length, the only possible values should be non-negative numbers. This means that each vector in X gets a number which is positive or 0. And this map we get, we call a norm if it fulfills 3 properties. Since you already know metrics, you might easily guess some of the details here. For example, in A, we find the positive definite part, which means if we have the length 0, then this is equivalent for having the 0 vector. Or in other words, the 0 vector has length 0, which makes sense, but it's also the only one with length 0. Now part B explains what happens to the length when we scale a vector. Scaling here means we have a vector X and multiply it from the left with a scalar, so a number in F. In the picture you always visualize that with the arrow getting longer or smaller depending on lambda. Hence the norm has to satisfy this, which means the length gets also multiplied by this factor lambda. However, lambda could be a negative number or even a complex one, such that this only makes sense if we consider the absolute value of lambda. Now depending what f is, r or c, we have here the absolute value in the real numbers or in the complex numbers. Therefore, this part B now tells you that the norm is always absolutely homogeneous. So you can always pull out scalars, but outside of the norm they always get absolute values. Okay, so we are in a vector space. We have 2 operations, the scalar multiplication we had in B, and now in C we have to explain what happens under the addition. So let's look at 2 vectors X and Y. You already know how to visualize the addition in a vector space. You just put the 2 arrows together to get out a sum. Then you see the triangle here and you think that the length, the norm, should fulfill the normal geometry in this sense. This means that it satisfies the triangle inequality. It looks similar to what we have for the matrix, but keep in mind, here it's with respect to the vector addition. Therefore, the norm is not a linear map in general, because you can pull out the addition, but what you get is only an inequality. Now you might already guess that a vector space together with a chosen norm gets a special name, and you are right. This pair is what we simply call a normed space. So what we have is a real or complex vector space where we can measure the lengths in a meaningful way. Now you might ask, what is the connection to the metric spaces we defined at the beginning of this video series? Since the property A and C look very similar, a norm could be a special case of a metric. Indeed, this one is an important fact you always should remember. If you have a norm for the vector space X, you can immediately define a metric. So maybe let's put the norm in the index of the metric, and then we can define the distance between 2 points x and y. If we look at the elements of the set x, we should think of the endpoints of the arrows. And then the distance between the 2 points should be given by the connection vector, which is x minus y, and then we take the length of it. In fact, this then defines a metric for the set x. This one is not hard to show. I advise you to try it out. So proving the 3 properties of the metric by just using the 3 properties of the norm. Now the most important thing to remember here is, because we always have this definition in mind, a norm space is indeed a special case of a metric space. In particular, all the definitions we have for metric spaces also work for normed spaces. So for example, closedness, openness, and so on. And with this in mind, we can now eventually define what a Banach space is. So it could happen that our new metric space here, XD, is a complete one. This one is a very nice property, which we discussed in the last video. All the Cauchy sequences converge. We don't have holes in this metric space. In this case then, the original norm space, X with its norm, gets a special name. We call it a Banach space. Okay, so now you know the definition of one of the most important objects in functional analysis. So you see, we have ingredients from the algebraic side and also from the analytical side. On the one hand, we have a real or complex vector space, and on the other hand, we have a complete metric space. And the thing that connects both sides very smoothly is our norm. So please keep that in mind. We don't have any metric here, we have the metric that comes from this norm. And by definition, the norm can deal with the algebraic operations. So this is how I see a Banach space in the abstract sense. To get more concrete, we will look at a lot of examples in the next video. So thanks for listening, and I hope I see you there. Bye!